Hi everyone, my name is Shu Xiao, currently a postdoc at UT Austin, and I will be joining the computer science department at George Mason University in fall 2022, so I'm looking for grad students. But today, I would like to talk about our paper at UT Austin, Learning Inverse Kinodynamics for Accurate High-Speed Off-Road Navigation on Unstructured Terrain. This paper is joint work with Jordi Biswas and Peter Stone. The motivation of this work is this realization that high-speed navigation really becomes challenging under three combined adverse conditions. First, if you want high accuracy. For example, if you have a pre-specified trajectory you would like to follow, such as for obstacle avoidance or to reach certain waypoints in the workspace for a navigation task. And two, you also want to do it at very high speed, where you really need to go beyond pure kinematics and consider kinodynamics. And three, if you also want to drive off-road on unstructured terrain. Here is the problem setting. We have a desired trajectory we would like to follow with high accuracy and with high speed. We feed that trajectory into our controller. The controller will compute some controls U, which runs through some forward kinodynamics function in the real world dependent on some world states W from the environment, and then result in some states of the robot to follow the desired trajectory. The controller objective we have here is that, say we have a trajectory we have to follow with high accuracy, showing in blue here. What we want to optimize is the total time it takes to traverse the trajectory T, and also the accuracy of our execution, which is shown in red. So we want to also penalize the difference between our executed trajectory and the desired trajectory, because you may want to avoid obstacles on the way, and you may want to hit certain waypoint you need to reach as part of the navigation task, and so on. So what's the problem with this? The problem is that the forward kinodynamics model depends on a lot of unknown world states. For example, the kinodynamics may be different when the robot is driving on mud, on grass, on cement, or on grass with leaves, on roots with twigs, or on cement with leaves, etc. And these things really motivate how the car really behaves in the real world. So what can we do about this? There are some conventional school of thoughts to address this problem. First, let's assume you have some sensors on board the robot, and you have some observation functions that can give you observations Y as a function of the car state X and world state W. Then you can do some form of terrain classification to understand what kind of terrain you are trying to drive over. Previous approaches have used, for example, vibration-based methods such as using IMUs, inertial measurement units, or using vision-based methods like RGB cameras to classify terrain into different types, discrete different types. When you know the type of terrain, the discrete type of terrain you are driving on, you can use a terrain-specific model to feed into your controller to solve this problem. But what we are going to do here is something slightly different. Instead of a discrete set of multiple predefined terrain models, we are going to learn a continuous all-terrain inverse kinodynamic function. And also, instead of manually craft appropriate models for different terrain classes, we learn our continuous all-terrain model in a data-driven manner. The key of doing that is essentially including sensor observations Y in this inverse kinodynamic model, F inverse, to capture the true world state W. This will allow the inverse kinodynamics model to consider the world state, which is still not directly observable, but by considering onboard sensor observations Y, these unknown kinodynamic effects can be learned by the robot. So how do we actually learn these kinodynamic effects based on onboard sensor observations? We learn those using some off-track time. By off-track time, I mean we manually drive the robots in an open space, not on the track we are going to eventually deploy the learned inverse kinodynamic model, but just on different terrain types. And what we collect are joystick controls U, the state of the car X, onboard observation, sensor observations y, and the actual outcomes from real-world forward kinodynamics delta x, all indexed by time step I. We don't know what the real-world forward kinodynamics function is, but we can just observe what actually happens in the real world and collect the output by rolling it out in the terrain, on the terrain we are of interest. And then we train a regression model with this as supervised loss. In particular, we play this game by reversing the input and output of our system. We pretend the actual outcome, delta xi, collected by rolling out in the real world is what we actually seeking. So in order to get the control input from the approximated inverse kinodynamic model F plus parameterized by theta, the regression model would tell you that if delta xi is what you are seeking, the control input to result in that is the joystick command UI we just collected while executing this. To implement this, we implement our approach on our UT autonomous robot, which is a scale 1/10 autonomous mobile robot platform with Ackermann steering, and there's also four-wheel drive. It has an onboard Hokuyu 2D LiDAR for localization on a pre-mapped geometrical map, and a vector nav VN100 IMU to provide the observations Y that capture the unknown world state W. In particular, the learning model we use is a neural network architecture shown on the right. The neural net takes in the last 100 IMU measurements, including accelerometer and gyroscope spanning over the last half a second. So all of these go through an autoencoder to a two-dimensional embedding space, showing blue. This two-dimensional vector is concatenated with the desired change rate of the robot state, so delta x, shown in orange. And then this concatenated vector is fed into two fully connected layers, showing purple here, whose output is the total inverse kinodynamics response, or the control input we want to derive, U. So we are learning jointly both an embedding function, showing blue, which is essentially mapping from how these sensor observations are allowing the robots to reason about what's different about this type of terrain, and modify that in the following actual inverse kinodynamic layers, showing in purple, which is the actual, which will output the actual control input U. We implemented this on an actual off-road track with multiple types of terrain variations, including, for example, cement, mud, grass, and leaves, and also tree branches and twigs of different kinds. So we compare three different methods, three things. The first one is shown in red. This is a baseline model which has no learning involved at all. So it is a hand-designed static kinodynamic function, which is one model fit all the terrains. The second one shown in blue is an ablation model, which is a learned one. It's a learned model, but without considering the sensor observation input. So that is one learned model that also fits the entire terrain, but it is learned, so the actual response is actual real terrain interaction from the real world. So we want to show that the sensor observation inputs are actually very important to learn terrain-specific modifications of the kinodynamic function. So this blue approach may not work very well because it treats all the terrains as the same using one single learned model. And the last one showing green is our learned model with sensor observation inputs. So we try these three approaches with different speeds from 1.6 meter per second to 2.5 meter per second. That's the target speed the robot is trying to achieve to drive as fast or as close to this target speed as possible. And we plot the actual executed trajectories of 10 laps each speed on the map, on the track. We compare with the desired trajectory. It is a segmented line shown in black. So in general, the executed trajectory becomes more scattered with increasing speed for all three methods. This makes sense because when you're driving fast, there's more stochasticity being introduced into the system, so the trajectory is less predictable. But in general, however, as you can see in these graphs, The green trajectories are always the closest to the desired trajectories, while the red ones are always the farthest away, no matter how scattered they are. We also show the number of failure cases at each turn. So whenever the robot makes a turn, there's in all turn 1 all the way to turn 8 different turns in the map. So whenever the robot makes a turn, there's a chance that it won't be able to successfully make the turn. So that's a failure. So the failure can be caused by, for example, collision with the track, or just getting stuck, kind of find a feasible motion to come out of the turn. So the size of the circles, the colored circles at each turn indicates the number of failures. So the bigger the little dots, the circles, the more failure cases it's actually encountered in that turn using that specific method, color coded by the red, blue, and green colors. You can see the failure number increases in general with speed. That is not surprising because it's more stochasticity. But the red circles are always larger than the blue ones, which are larger than the green ones. So this means our method, the green method, has the highest success rate when driving at different speeds compared to the ablation model and also to the baseline model. Going a little bit more quantitatively, we plot the actual failure turn rate per speed and also actual failure turn rate per turn, both on the left and on the right. So first on the left, you can see the red baseline has the highest failure rate in all different speeds, from 1.6 meter per second to 2.5 meter per second, while the green learning-based methods we introduced has the lowest failure rate. It also outperforms the blue ablation model, which justifies that the sensor observation is the key to reason about different types of terrains. In terms of failure rate at different turns, shown on the right, we can observe the same trend from the three approaches. In all the turns, the red baseline fails the most, while the green learning-based approach, which takes in account the sensor observations, achieves the lowest failure rate. We also deploy our learned model from the outdoor terrain to an unseen indoor terrain, which is basically my living room, so it's presumably an easier terrain. Note that the track layout is always unseen. It's a different layout, it's always a different layout, because we train the model with data collected during off-track time. You can see the green learned model comes closer to the desired trajectory, and the red failure dots are much larger in all 4 turns compared to the green dots. You can also see similar trends in terms of the failure turn rate per speed and per turn in this unseen terrain. The learned inverse kinodynamic model performs much better than the baseline handcrafted model. Of course, we speculate that the generalization would not be as good if the model were trained indoors on easy terrain, but applied outdoors. So I would like to share a video of the robot executing the learned model. We can see the robot taking these turns in a very aggressive manner, and there is significant slippage between the wheels and the terrain. Those are not very easy to model, and you cannot easily come up with different manually designed, manually crafted inverse kinodynamics model to capture that. But our learned inverse kinodynamic model can actually account for all this by considering the onboard IMU observations to modify the steering function to be able to precisely drive on different off-road terrains at different high speeds. As you can see on an unseen terrain in my living room shown in the lower part of this video, it also drives more successfully. So in conclusion, we show that using inertia-based onboard observation embeddings, we can capture these unknown, oftentimes elusive and stochastic world state impact during off-road navigation on unstructured terrain. We also show that you can learn these inverse kinodynamic models for accurate and high-speed off-road navigation in a data-driven manner. And you can see an improvement in terms of navigation in both seen and unseen terrain and with unknown arbitrary track layout. In future work, we want to expand these observations, so instead of just using IMU measurement, we also want to use vision input, which can give us the potential to look ahead and adapt to future terrain in advance. Of course, we would like to investigate how to generalize from easier to harder environment. With this, I conclude my talk, And lastly, I would like to put out an ad for potential graduate students. Since I'm joining George Mason University in fall 2022, if you're interested in pursuing a master or PhD degree in robotics, motion planning, and machine learning, especially with a focus on field robotics, such as the terrain-aware inverse hemodynamic planning work I presented in this talk, I encourage you to apply to the graduate program starting fall 2022 in the Department of Computer Science at George Mason University. Feel free to shoot me an email to discuss more details.